my name is Elena Gofas, and thank you very much for having me today. I'm a researcher at Insitut de la Vision, and I want to talk today about developing high-resolution imaging of the retina with the goal of studying neurodegenerative diseases. So I just wanted to introduce myself real quick. I'm an optical engineer, and I later specialized in biomedical engineering. And then I did my PhD at ONERA, which interestingly is our space lab. So I learned techniques that are historically applied for astronomy and telecommunications and in the medical field. And then for my postdocs, I focused on the taking microscopy techniques and applying to in vivo imaging. So I work at the Insitut de la Vision and particularly in the photonics department, and our team specializes in cellular imaging for the patient. And this includes in vivo ophthalmoscopy, but also work in microscopy. And I was thinking about this training and especially this research axis when we're talking about going from the physical principles all the chain of the making an image to the end. And actually, this is also how we worked a little bit. Our goal in our team is to develop safer, faster, and more elaborate diagnostic tools too. And our team belongs to a larger network, which is called Paris Eye Imaging, and several institutes belong to the network. And the idea is that we have an idea, and then we develop a proof of concept. We test it, and if it works, we try to do clinical prototypes and systems. But more importantly, we try to work very closely with other specialists. We're not only physicists or engineers, we try to work with biologists and especially directly working with clinicians. So all the development of the imaging system are done in collaboration with them. And particularly when we think about developing imaging system for the medical field, one of the biggest challenges is that we have to think about developing it for the clinical setting, which has very particular challenges, and having obviously quantitative characterization of our images, and it has to be robust. And so to do this, we develop actually our system directly in the hospital. And I think this facilitates a lot to adapt them directly to imaging in the patient. So in my case, I really focus on the development of system to study neurodegenerative diseases. And I think it might be interesting for people why I am looking at the retina and why I'm looking at the eye. And in fact, the retina can be seen as an extension of the brain. And so it's also affected by neurodegeneration when there is degenerative diseases like multiple sclerosis or Alzheimer or all these known diseases. But more importantly, it's the only non-invasive access to the neurovascular network. So it's a really great opportunity to look in vivo at the neural network. So when we think about developing in vivo imaging system, here my aim is to reach the cell detection during neurodegeneration. And once I'm seeing the cells that are being degenerated, I want to characterize them. And so these imaging systems are useful for a clinical application. So when we do cellular imaging of the eye, there are several challenges. The first is that when we do an image of the retina, the image is blurry. And this is due to the aberrations that are generated by the optics of the eye. The other big challenge is that the light backscatter from the retina is very low. We have a very little amount of light that comes back to the detector. And also the fact that the retina is a thick sample, so it has several layers, so we can have multiple scattering in the retina. So these are the challenges that we have to look when we're trying to do cellular resolution and also high contrast in the retina. But as I was saying, when we're thinking about doing something for a clinical application, we also have to think ahead. What are the challenges that we're going to be facing once the system is built and we want to put it in the clinic? So unlike microscopy, when you're looking at the patients, you have to be aware that we cannot put any amount of light in the patients. We have to be aware of the safety norms. And also patients might have, because of the pathology, can have bad fixation. The tissue of the retina can be affected by this pathology. So if we design something that it's for healthy retina, it might not be applicable to the patients. But also we have to be mindful that patients have very little time in a hospital. They have many tests, so it also has to be an imaging system that is fast. So when we are designing our imaging system, actually we're mostly working a little bit at all of the things at the same time, so we can think about all these challenges when we're developing the system. Okay, so I'm gonna start a little bit to explaining what we're doing to reach first high resolution in the retina. So these are two typical clinical images that you can get in ophthalmology. One is the fundus eye, so it's just an image of the eye in a full field camera. So you can see the bigger features like the vessels, the optic nerve, and if you have an atrophy that is big enough, you can see it develop here. Then one of the biggest breakthrough in ophthalmology is the optical coherence tomography. And so you cannot see the cells, but you can distinguish the different layers here. The epithelium, pigmented epithelium, the photodetectors that converts the light from light to electric signal, and then all the inner neural layers. And then finally the light goes back to the brain through the nerve fibers. So the fact that we cannot see the cell is due to the lack of resolution, and this is due to the, as I said, to the aberrations generated by the optics of the eye. So to have a bigger resolution, we have to increase the size of the pupil, but as we increase the size, we also increase the effect of the aberrations on the image. And so to solve this, we use a technology called adaptive optics that comes from astronomy. And this technology is going to be used to correct for this aberration, correcting the wavefront, and then obtaining diffraction limited resolution. So I wanted also to discuss how do we choose a little bit the type of choices that we do when we were developing the systems. So the first thing is that there are different types of adaptive optics. There's hardware and also computational, but here I'm just going to talk about the two hardware options. One option is the sensorless adaptive optics. This means that we're not going to be measuring the aberrations. We're just going to be, we're going to choose a quality metric of the image, and then we're going to be applying corrections to correct the aberrations, and then we're going to stop when this metric is maximized. This type of adaptive optics is very good when you have aberrations that do not vary very quickly, so because it only provides a slow correction. And this is not the case for the retinal imaging, because with the tear layer of the eyes and the fact that we are moving, so we're constantly moving the part of the pupil that we're imaging, we have quickly varying aberrations. So we use the second type of adaptive optic, which is the wavefront sensor aberration. So for this type of adaptive optics, we use a wavefront sensor to measure the aberrations, and then we apply a correction in a closed loop. And so this is better adapted for retinal imaging because it's more appropriate for fast temporal variations of the aberrations. So how does it work in our system? We send light to the retina, and then the light is scattered back. It is scattered back by aberration. It's an aberrated wavefront due to the optics of the eye. And so this light is going to be analyzed using a wavefront sensor. So there's a different types of wavefront sensor, but the most commonly used is the Schack-Hartmann. The principle of the Schack-Hartmann is that we image the light through a micron lenslet array, which is going to focus each a little bit section of the wavefront in front of a lenslet. And so in the case of a perfect wavefront, so in the case that there's no aberration, the light is focused in the optical axis of the lens-led array. However, if you get aberrated wavefront, this focalized point is going to shift, and by measuring this shift, we can estimate the aberrated wavefront. So then we take this measurement, and then we compute the tensions that we have to apply to this deformable mirror. And this deformable mirror, we're going to apply a shape that is opposite to the wavefront aberration, and we're going to correct the wavefront. So this is going to lead to increase in resolution, and we're going to be able to reach cellular resolution of the ophthalmic camera. So adaptive optics can be applied to many cameras in ophthalmology. It has been applied to OCT. So here we can see that OCT becomes very defined with the cells, and it has also been applied to ophthalmoscope. Here, full field and also confocals, and we can see the individual photoreceptors. So we had the options of choosing between many of the ophthalmic cameras. So here we had to think what was our aim. And our aim is studying the neurodegeneration, so the different neural layers. So we wanted a system that had a good optical sectioning and also was very fast to be adaptable to the clinic. So this is why we chose the adaptive optics scanning laser ophthalmoscope. And so the idea, the reason that we chose it is because of the confocal detection. So this system scans through the field of view to get the whole image. And because of the confocal detection, we are able to filter out all the out of focus light. And so we have very highly contrasted layers that are highly reflective. So here, for instance, we can see the fiber bundles of the retina. We can see the photoreceptors, the different capillaries, but also we can also implement other modalities, for instance, confocal autofluorescence, where we can see the RP. The problem is that for neurodegeneration, when we're thinking about, for instance, multiple sclerosis or Alzheimer or all of these diseases, we are more interested in these layers, which are the ganglion cell layers or the bipolar cells, and are the ones that are seen to be affected when there's atrophy apparent in the retina. But the problem of these layers is that they are transparent. And so unlike histology, we cannot go and mark inside of a patient. So to address this challenge, we had to change the AOSLO, and we have to develop a new modality, which is called phase contrast. And the idea is that instead of scanning with a confocal pinhole, we're going to shift this pinhole to an offset position. So we're going to block the confocal signal, and we are actually going to detect the out of focus signal and the multiply scatter signal. So the hypothesis is that when we send light to the retina, the light is multiply scattered by deeper layers of the retina, and it's multiply scattered back towards the detector. And then this light goes through this transparent cell, and depending on the index of refraction of the tissue where the lights arrive, the light is going to be deviated by different angles. And so at the detectors, we're going to detect more or less light depending on this deviation, which is related to the index of refraction. So this translates into the detector by changes in intensity. So here, for instance, is the same layer. You can see in the confocal, you can see the highly reflective signal of the nerve fiber layers. And using the phase contrast, we have this sort of phase gradient. So this is the difference between these two detectors to create the gradient. And so you can see with details the capillaries, but also in the background you can start seeing the shapes of the ganglion cells. So these, we didn't invent anything. These are techniques that are highly developed in the microscopy field. We just wanted to adapt it to in vivo imaging. So we still needed to improve this imaging because we can guess them, but it's hard to really segment or see them correctly. So during my postdoc, I worked on trying to find the optimal pattern of detection in offset to get a higher contrast. So I looked at the scatter, and I also defined image quality metrics such as SNR or the energy of the ganglion cells. And I was able to detect with a much better contrast the ganglion cells, but also we were able to detect some other features like what seems to be macroglial cells. And thanks to the fact that we had a high temporal resolution, we were even able to follow them a little bit around the vessel. So I installed the same optimal pattern in the AOSNO at the Kansman Hospital. Um, I was able to reproduce the ganglion cell images, but more importantly, I was able to introduce this system into clinical protocols, and in particular to clinical protocols with multiple sclerosis. And so we were able to detect for the first time in this disease these cells that when we compare to what our colleagues are doing on the mouse, where they induce inflammation and using the same technique, they are very similar. They are round shaped with compact cytoplasms and with um, some intracellular features that could be nuclei. So this is a little bit where we are right now. We have been able to reveal previously transparent and invisible cells in the ganglion cell layer, and also during what seems to be inflammation. But the problem is that although we can make hypotheses on what these cells are, we still, because we're working in the medical field, we still need a stronger validation. So all our work right now is also trying to find ways of characterize these cells. So of course, the first easier, let's say, more evident is to keep imaging people and to keep computing metrics to try to characterize the different cells by shape. For instance, their diameters or their distance to the vessels and this sort of metrics. But also, we can follow actually many of these patients over time. So we're also trying to see if we can characterize the dynamic of these cells. For instance, here we can see these cells during the same imaging session. Then we were able to catch one cell for a patient that came 3 times in the same day. And then we can also, for instance, characterize the changes in density in the same layer for these cells. So the second work that we're trying to do is try to use histology to see if we're able to compare. But it's really hard because most of histology people use the immunolabeling, which is very different to what we have. However, historically, there has been phase gradient imaging in histology. So we're trying to come back to that. We're trying to image the retina using this similar phase contrast technique to try to compare with the same metrics, morphological metrics in vivo and ex vivo, and then superimpose the markers and try to see if we are able to better characterize what we're seeing. So also, one interesting thing is that our colleagues in microscopy, for instance, here in oblique microscopy, they also have this kind of gradient images, and they have been able to achieve quantitative phase imaging that they have used for labeling and also to extract some of the tissue's features. So an idea that we had is that we're going to try to model the multi-offset image formation and try to achieve in vivo quantitative phase imaging. And so the idea is to extract quantitative information from these images and try to classify maybe in the future if there's healthy or pathological. And I don't know if, yeah. So I'm actually done with the part where we're doing about neurodegeneration, and I wanted to take this opportunity to also talk about other development of imaging tools that we're doing. Particularly, I've talked a lot about structural imaging, but we're also developing functional imaging. In this case, we're trying to develop optoretinography as a way. So optoretinography, the aim is to see if the photoreceptors are still functioning or not. And so the idea is to send a light stimulus and observe the reaction. And so the idea is uh, to remove electroretinography, which is used until now for looking at if there's still function, because it's much more non-invasive. So this has been done on several systems, adaptive optics, so in AOSLO in the past, but also in AOCT, where they apply a light stimulus and they can see a shift in the length of the photoreceptors. And it has also been applied in full field OCT and other system in other ophthalmic camera. So our idea is to develop this at the hospital so we can apply to the patients with neurodegeneration and other retinal pathologies. And finally, I wanted to talk another work that I'm working on, which is transclear flood imaging. And this work, actually, it's interesting. We, instead of illuminating through the pupil, we illuminate through the sclera. And this is it's a system that has been developed by Imaginize, which is a French company. And the idea is that by going through the sclera, we don't get the very highly reflective light from the photoreceptor layer. And we are able to detect this layer that in the past we only were able to image it with autofluorescence, which requires very long illumination time. So here we can distinguish single cells. And I want to thank you for your attention. And I want to thank especially Creatis and Manutech for inviting me today.